The third section in Chapter 7 discusses atomic spectroscopy and the Bohr model. So by atomic spectroscopy, it's the types of light that atoms absorb and emit. Here you'll see the helium spectrum and the barium spectrum. You'll notice that in these spectra, you see a bunch of individual lines or very specific colors of light that the atom absorbs and emits. Atoms, it turns out, have what we call line spectra. Spectra is the plural of spectrum. So basically, atoms just emit very specific lines of light only. Specific types of light only. That's in comparison to a continuous spectrum. If it emitted every different color of light, it might look more like this continuous spectrum. So why is it that atoms have these line spectra and not continuous spectra? Well, it turns out that if we imagine in the middle of an atom you have the positive nucleus, surrounding that atom, the electrons in the Bohr model were described to be traveling around in specific orbits. So an electron could be traveling around in this circular orbit, or maybe it could be traveling around in an orbit that's a little further away, or maybe traveling around in an orbit that's a little further away. So this is the Bohr model for the atom. And again, what it says is the electron travels in orbits around the nucleus. So orbits like how the planet travels, or the planets travel around the sun. It can be a close orbit, or it can be an orbit that's further away. But only specific ones. It's never traveling in between those orbits. It's only in those specific pathways. So how does that relate to spectra? Well, if the electron moves from one orbit to another, so for example here, the electron, if it moved from one orbit to another, the orbits have different energies. And in order to go from one energy to another, it's got to get rid of that extra energy or absorb it. It turns out that for this particular atom, this transition between the third and the second orbit correspond to red light. Or the transition that goes from here to here, which is a bigger jump, corresponds to blue-green light, or the transition from even further out and down, a much bigger transition, corresponds to violet light. So because the electron can only travel in one orbit or another, that means that it can only make certain transitions between them and is only going to emit specific colors of light. So according to Bohr, you get these line spectra because the electron can only transition between specific orbits. And each atom has different orbits, so each atom has specific lines of light that it absorbs and emits. For example, we know that the sun is made mostly of hydrogen and helium, not because we've gone and taken a scoop of out of the sun and analyzed it, but because we can see what kinds of light it emits and absorbs. Another way to look at these orbits is each one has a different energy. And the orbit that's closest to the nucleus, n equals 1, has the lowest energy. Here, the energy scale at the top, it's higher in energy. At the bottom, it's lower in energy. So the one that's closest to the nucleus, remember that the negative electron likes to be close to the positive proton, is the best, the lowest energy. So that one's low energy. And then as you get further from the nucleus, you get higher energy. And there's an equation in your textbook. E sub n is equal to negative 2.18 times 10 to the negative 18 joules over n squared, where you can calculate these various values of energy, the units of energy in joules, which is where this J comes from. So you can calculate what these energies are. If you go all the way up to n equals infinity, which n it continues to increase 1, 2, 3, 4, 5, 6, 7, 8, etc. If E for n equals infinity is this number over infinity squared, if you divide by infinity, that ends up being equal to 0. So the energy of the electron when it's completely gone from the atom, an infinite distance away, is 0 joules. All other energies are less than that, and you might notice that they all have these negative signs because 0 is where the electron is by itself. Being with the positive proton is better, lower than 0, negative. So if we look at different transitions, so for example, these are the transitions that hydrogen makes. When the electron falls down, it's got to spit out extra energy to get rid of that extra energy. These transitions correspond to visible light. So we see red, green, and violet. If the transitions were less energy, we would see infrared. Well, we wouldn't see it, but infrared light would come out. And if the transitions are really, really big energy transitions, more energy than visible or infrared would be ultraviolet. So these different waves, infrared is longer wavelength, visible is somewhere in between, and then ultraviolet would be very short wavelengths. So long wavelength, short wavelength is kind of the difference there. If it's longer wavelength, it's going to be low frequency. The symbol for frequency is the Greek letter nu. If it's short wavelength, it's going to be high frequency. More of these waves pass by per unit time. And low frequency means low energy. High frequency means high energy. And you can imagine that if a wave is going up and down like that, that's higher energy than a wave that is just kind of loping up and down, something like that. So, to give another example of this, we'll move to some blank space. If we wanted to look at the energy change between two levels, you might have seen in your textbook the equation delta E is equal to negative 2.18 times 10 to the negative 18 joules, 1 over n final squared minus 1 over n initial squared. If you transition between two levels, let's say n equals 5 and n equals 2, if you start at n equals 5, that's your initial. If you end at n equals 2, that's your final. And when we go down from here to here, if this is high energy and this is low energy, in order to go from high to low, it must give off or emit energy. And one way to give off or emit energy is as a photon of light. These photons of light or particles of light are equal to energy. And if we plugged in 5 and 2 into our equation, we would find that the change in energy, negative 4.58 times 10 to the negative 19 joules, it spit out that energy, and the fact that it's given off is represented by the negative sign. So if you give off energy or emit it, that change is going to have a negative sign. If later on we went to go calculate the wavelength or the frequency of the light emitted, the energy of a photon is always going to be positive. So for this, you're going to ignore the negative sign. So if we went to calculate frequency, E equals h nu, or if we went to calculate wavelength, E equals h c over lambda, we would ignore the negative sign because the delta E equation is the change for the atom. The energy of the photon, the photon is the energy, so it's never negative. And you shouldn't have a negative wavelength or a negative frequency. Conversely, if you went up instead, so if we did go up instead, that would be a positive change. And again, going down is a negative change. So down loses energy, negative, up gains energy, positive.